Okay, so we're very happy to have Yoon-Joo Kim here today in the Western Hemisphere Virtual Symplectic Seminar from the University of Bonn, and he's going to tell us about the dual Lagrangian fibrations of compact hyper-Kähler manifolds.
Yeah, thank you for the invite. I'm glad I can, speak here in the Western Hemisphere Virtual Symplectic Seminar. I should tell you before I start to talk, I'm not a symplectic geometer. I have like almost no symplectic geometry background. I'm really sorry, but yeah, hopefully, this talk is about algebraic geometry / complex geometry. Hopefully, I can, tell you something interesting in terms of like symplectic geometry or something like that. Anyway, so let me start. So I want to talk about compact hyper-Kähler manifolds and their Lagrangian fibrations, especially the notion of their dual. Okay. So let me let me tell you what a compact hyper-Kähler manifold is. So as you can see, the compact hyper-Kähler manifold, sometimes called an irreducible holomorphic symplectic manifold, because, I mean, if you see the definition, it's just like a holomorphic version of a symplectic variety. Anyway, so my formal definition of the compact hyper-Kähler manifold here is a compact Kähler manifold. So I want to sort of give you a warning that the compact Kähler manifold here, as an algebraic geometer, I don't want to fix Kähler form. I fix a complex, what's it called, a complex structure on the manifold, but I don't fix the Kähler form. So that's my compact Kähler manifold, such that there's a unique global holomorphic 2 form of the scalar. So in an algebraic geometry notation, it's like that. H20 is generated by a single sigma, and I require this sigma, the unique holomorphic form, is non-degenerate every point, which is precisely saying that it is a holomorphic symplectic form. And then the third condition is just a topological condition. I want to require this hyper-Kähler manifold is simply connected. Okay, that's my definition. So let me tell you why this hyper-Kähler manifold theory thing is potentially interesting. So historically, hyper-Kähler manifolds are first introduced by Berger. Well, I mean, Berger classified the sort of a Riemannian manifold in terms of the holomorphic groups, and hyper-Kähler manifolds arose one of them. So that's a background. So as you can see, Berger classified the possible holomorphic groups of simply connected Riemannian manifolds, and then I think there are like 7 or 8 of them. I forgot the precise number. The first one being orientable manifold. The second one, holomorphic group UN, it's called a Kähler manifold. Third one, Flavial, and the fourth one, here it goes, our hyper-Kähler manifold, which is the main interest in this talk. So that's historically the first moment when hyper-Kähler manifold appeared. And in algebraic geometry context, a hyper-Kähler manifold is actually rediscovered later in the 1980s in the following theorem proved by Bovila and Bogomolov. So what's a theorem? So the theorem is that if you start from a compact Lagrangian manifold, meaning that your canonical bundle is trivial, it's a complex manifold, and then basically up to some covering issue, it has to be a product of complex tori and hyper-Kähler manifolds and what's called strict Lagrangian manifold, which is like a remainder thing. So as you can see, hyper-Kähler manifolds arise one of the building blocks of this Bovila decomposition theorem. So that sort of justifies why hyper-Kähler manifolds can be potentially interesting. Okay, so well, this is also a justification thing. So you can think of abelian varieties or complex tori as a higher dimensional generalization of the elliptic curves. And in that sense, hyper-Kähler manifolds generalize the notion of K-free surfaces. So hyper-Kähler manifold you can think of as a higher dimensional generalization of a K-free surface. And then, yeah, actually many properties of the K-free surface just directly generalize the hyper-Kähler manifold. That's really surprising because, K-free surfaces are dimension 2 surfaces, which enjoys a lot of properties because of that. But hyper-Kähler manifold somehow, even if it's a higher dimensional variety, it enjoys a lot of similar properties to K-free surfaces, as if it is a surface. So an example of a hyper-Kähler manifold is a K-free surface, of course. The dimension 2 hyper-Kähler manifold, I told you that's a K-free surface. And then one easy to construct example is the following. So you start from a K-free surface S, and then you can consider what's called a Hilbert scheme of 2 points on that K-free surface. And my notation for that is S to the upper bracket second power. That's my x. So what is a Hilbert scheme of 2 points? If you've never heard about that, it's sort of a moduli space of 2 points on the given K3 surface S. So that's like very similar to the symmetric power of the second symmetric power of the K3 surface. Yeah, it's like a resolution of a moduli space of 2 points. This is more or less the Hilbert scheme, at least in our case. And it turns out this is a non-trivial theorem. It turns out this is a hyper-Kähler fourfold. You got to prove this is simply connected, and it has a unique holomorphic symplectic form, and so on. But at the end of the day, it is hyper-Kähler fourfold. So that's the most easiest example. And the second easiest example is what's called a generalized Kummer fourfold. So what is this construction? So you start from an abelian surface in this case instead of the K3 surface. And then you consider the Hilbert scheme of 3 points on an abelian surface, following the same notation. And then because the definition of the Hilbert scheme of 3 points is just basically a moduli space of 3 points, every point here can be expressed in terms of a triple x comma y comma z, so that you can consider the summation map because you start from an abelian surface, right? So if you consider the summation map from this Hilbert scheme of 3 points to the original abelian surface, and then it turns out this is a fibration. This is an isotrivial fibration, and then if you take the fiber of that, it becomes a hyper-Kähler fourfold. It's also a non-trivial theorem proved by both of them. Okay. Right. So, and if you've been to some other hyper-Kähler manifolds talk, and you always see this kind of slide. So unfortunately, that's basically all we know about known examples of hyper-Kähler manifolds. So hyper-Kähler manifolds are extremely difficult to construct. So basically, the former two examples, the K3n type, the Hilbert scheme of n points on a given K3 surface, and the generalized Kummer construction, where I replace this Hilbert scheme of 3 points into the Hilbert scheme of n plus 1 point, and then I get the same construction. That's called a generalized Kummer variety. So those two examples turns out to generalize to higher dimensions, arbitrary 2n dimensions. And there are two sporadic examples, what's called O'Grady 10 and O'Grady 6, which are, as you can see, 10-dimensional and 6-dimensional. Those are like complex 10-dimensional, complex 6-dimensional hyper-Kähler manifolds. And then basically those 4 examples are all known examples at this point. People have been working on this for 20 years, but then, yeah, since the last discovery of O'Grady 6 type, for 20 years, nothing, no progress. People weren't able to find that. Okay, so that's all currently known examples. So any questions so far? Good. Okay, so let me talk about Lagrangian. Of course, symplectic geometers are experts in Lagrangian fibrations. Why would I? Let me just talk about Lagrangian fibration in a complex geometry setting. So if you know the K3 surface theory, then there's what's called an elliptic fibration of a K3 surface, which plays a very important role in the K3 surface theory. So let me recall you the definition of an elliptic fibration of a K3 surface. So you start from a K3 surface S, and then you have you consider a fibration pi from S to B, where B is a complex manifold. Okay, and I want to consider a non-trivial fibration, meaning that I want to exclude these kind of trivial fibrations where pi is an identity map, which is obviously a fibration, but is kind of dumb. Also, you want to exclude the trivial fibration from S to a point. That's also not very interesting. So if I exclude those two kinds of the stupid examples, and I call them non-trivial fibration, where the fibration means that all the fibers are connected. And then there's a proposition, it's kind of easy to prove, that your complex manifold B turns out to be dimension 1, and also it's always CP1. That's a proposition. And the second proposition is that all the smooth fibers of pi are forced to be elliptic curves. That's a second proposition. And because of that reason, we call this fibration, any non-trivial fibration from a K3 surface, an elliptic fibration of a K3 surface. And everything is holomorphic, so this is a holomorphic fibration. Right, so this is well known. So this slide may be slightly less known to non-hyper-Kähler people. So it turns out this previous theorem or proposition actually generalizes to higher dimensional hyper-Kähler manifolds. So what's the statement for the higher dimensional hyper-Kähler manifolds? So if you start from hyper-Kähler manifold of dimension 2n, which is my x, and then you have a non-trivial fibration from X to a complex manifold B. I, don't want to consider stupid examples. Then that forces your complex manifold to be isomorphic to CPN. And also, all the smooth fibers of pi are necessarily abelian varieties of dimension half the dimension, and it's Lagrangian with respect to the holomorphic symplectic form. So because of that reason, we call that a holomorphic Lagrangian fibration index. Yeah. So yeah, this is a very surprising theorem because, for example, we haven't assumed anything about the dimension of B, but then if you just exclude the dimension 0 and the dimension 2n case, then just that forces the base to be CPN. So this is called Lagrangian fibration hyper-Kähler. Good.
I have a question.
Yeah, sure.
Can you say anything about singular locus? So you talk about smooth fibers, but how about singular locus?
That's a very hard question. So for K3 surfaces, the singular fibers are classified by Kodaira and Neron in like 1950s or 1960s or so on. And there's there's the whole classification, Kodaira classification of, you know what a classification is. But then for high dimensional, like even for hyper-Kähler fourfolds, well, okay, for hyper-Kähler fourfold, there is a classification by Matsushita. But hyper-Kähler sixfold and so on, it's a very hard question. There are partial classification. Yeah. Anyway, that's a nice question. Thank you for the question. Okay, so here's a typical picture, for example, for elliptic K3 surfaces. So if you have a K3 surface, elliptic fibration of K3 surface, where B is a CP1, then as Hang mentioned, there all the smooth fibers are elliptic curves, but there are exactly 24 up to multiplicity, exactly 24 singular fibers. And those singular fibers, we know what those are by Kodaira classification. For example, this is called a Kodaira type I1 fiber, 1,1 fiber, yeah, or this is 1,2,5, something like that. There's a notion, there's a notation. Right. So here's an example of a Lagrangian fibration of a higher dimensional hyper-Kähler manifold. So I told you if you start from a K3 surface S and then consider the Hilbert scheme of 2 points on the K3 surface, that's a hyper-Kähler fourfold. But if you start from an elliptic K3 surface S to P1 and take the Hilbert scheme of 2 points on both the S1 and S and P1, then that becomes a Lagrangian fibration of your hyper-Kähler fourfold S, second bracket. And the map is defined by sending x comma y to pi x comma pi y, which is, as is kind of an obvious map. Turns out this P1 second Hilbert power or the second symmetric power of P1 is isomorphic to P2. This is a well-known result in complex geometry. So that it doesn't violate the previous theorem that the base has to be P2, and then it turns out all the fibers are connected. So it's a Lagrangian fibration.
So question, on the previous slide, the second part of the theorem, I think, said that the fibers must be Lagrangian if they're smooth. Is it possible to give any intuition for why that's the case?
The second result?
Yeah.
Yeah, sure. So this is basically, let me think about it. Do I have a convincing, I think it's, why is Lagrangian? So the only proof that I know is, this is proof of Matsushita. The only proof that I know by Matsushita is kind of, I remember the proof, but it's kind of technical. So what you do is that you consider the intersection pairing of this sigma with respect to you fix a Kähler form, a hyper-Kähler form, omega, and then you consider the intersection pairing with the sigma, a bunch of power of the sigma and a bunch of power of the omega, and so on and so on. And then you prove those are 0, and then that will force this to be Lagrangian because you have what's called a Hodge index theorem. Yeah, but I don't know an easy way. I don't know an intuitive way. I'm sorry.
Okay.
Right. Okay. So that was the basics. So let me talk about what we're going to talk about. Yeah, the topic of this talk. So the goal of this talk, I want to remind you that the goal of this talk is that given a Lagrangian fibration of a hyper-Kähler manifold, I want to construct an appropriate notion of a dual fibration, and then I want to kind of justify that why there should be a dual fibration. Yeah, that's a goal of the talk. Of course, there's no precise definition of dual Lagrangian fibration and so on, but I'm like going to give at least one in my talk for Lagrangian fibration of a hyper-Kähler manifold only. And then I want to justify that may be the correct one. That's a goal. Okay, so as you all know, there's a 4-step or a 3-step construction of the dual Lagrangian fibration suggested by conjectured by Strominger, Yao, Zaslow. You start from a Lagrangian fibration. Everything is holomorphic, by the way, holomorphic Lagrangian fibration. And then what you do is you throw out all the singular fibers to make it a genuine torus fibration. It's a smooth projective fibration. And then you somehow dualize all these smooth fibers fiber-wise so that you can consider the dual torus fibration. And then somehow you need to compactify the dual torus fibration into a dual Lagrangian fibration. And then you need to justify that should be the dual of the original Lagrangian fibration, and so on. At least this is the Strominger, Yao, Zaslow conjecture that I understood. Okay, so what is a dual torus fibration? So this is just a recall. So in the previous theorem, I told you all the smooth fiber of this Lagrangian fibration pi has to be have to be complex tori or abelian varieties. So to simplify the situation, we pull out all the singular fiber and we consider the genuine torus fibration. Yeah, just pull out all the singular fibers, unnecessary fibers, consider the genuine smooth projective family of abelian varieties or complex tori. This is the torus fibration. And then the dual torus fibration should be some new torus fibration such that fiber-wise, they have the dual torus. That should be the dual torus fibration. So to my knowledge, there's a slightly different definition between algebraic geometry and symplectic geometry of the dual torus fibration. My dual torus is a dual torus in terms of the complex geometry. It's sometimes called a dual abelian variety. I don't know, symplectic geometers are using the same one. But anyway, so that's what I mean by dual torus. So here's the picture. So I start from a torus vibration, x0 to be 0, and then I want to somehow construct a new torus vibration x0 check to be 0, where fiber-wise, for example, these blue fibers, F1 and F1 check, those are dual to each other, F2 and F2 check, those are dual to each other. This is what I want to get. Okay. So the easier case is when pi 0, the original torus vibration has a holomorphic section. So assume that for simplicity, the original torus vibration has a holomorphic section. So in the algebraic geometry context, this means that this pi 0 is an abelian scheme. So this is just a word. What is an abelian scheme? It means it's a family of abelian varieties. But this family admits a section so that it rigidifies the family, and then it also respects the addition structure of abelian varieties. So this becomes a group scheme. So this becomes a family of abelian group varieties respecting the addition structure. That's what I mean by abelian scheme. And then there's an abstract theorem of the construction of what's called a dual abelian scheme. Okay, for a given abelian scheme in algebraic geometry. How do you construct that? You consider the relative Picard scheme. So this is called a relative Picard scheme. And what is this? This is the moduli space of line bundles of degree 0. So if you consider the moduli space of line bundles fiber-wise, and then somehow that gives you the notion of a dual abelian scheme, and then of course that's fiber-wise dual to pi 0 because I mean it's a dual abelian scheme. And then it turns out this is a well-behaved notion of a dual torus vibration, and this is pretty well known. The problem in a situation for hyper-Kähler manifold at least is that not every torus vibration admit a holomorphic section. So there are definitely a lot of examples of Lagrangian fibrations where this torus vibration doesn't admit any kind of holomorphic section. And also the compactification process is not clear if you adopt this definition. Okay, so that leads us to the case when pi 0 has no section. So assume that there's not a single holomorphic section of the original torus vibration pi 0. Then, well, this is not an abelian scheme anymore, but you can still consider the relative Picard scheme, the same moduli space of line bundles that just abstractly exists. So you can consider that, and one can check this as fiber-wise dual tori to the original torus fibration. So this is one possibility of the dual torus fibration. And then the point is that I don't want to take this as my definition of dual torus fibration. So why is that? Because, well, in my viewpoint, this is not a good definition because this construction always admits a holomorphic section. So if you consider the moduli of line bundles, then there's obviously always a trivial line bundle. And the trivial line bundle will give you a holomorphic section of this dual, whatever this is, the relative Picard scheme. And then I think that sort of doesn't match with the fact that the original torus fibration doesn't admit any holomorphic section. At least this is my this is my sort of reason why I want to think about a different one. But people may object. Any objection or any question?
Oh, I have a question.
Yeah, sure. Yeah.
So what do you mean by fiber-wise dual? So here you say.
Oh yeah. So let me go back. Yeah, let me go back to the previous slides. So this is my fiber-wise. Well, this is what I meant by fiber-wise dual. So I have another family such that every fiber, like the fiber over this blue point, the fiber here is this blue fiber, and the fiber here is this blue fiber, and those are dual to each other. That's what I meant by fiber-wise dual. Because those are abelian varieties, they can be dual. They're notion of dual abelian varieties, dual complex tori. Yeah.
Thanks.
Okay. All right. So there was a problem. So how do we tackle this problem? And that leads us to the notion of torsors. Okay, so I have to explain what a torsor is. So to do that, I need to explain the group scheme first. A group scheme, G to S, is a family of groups. Intuitively, it's just a family of groups, holomorphic family of groups, such that the identity varies holomorphically, and group operations inverses, they vary all holomorphically, and the group the group axiom operate the what's it called? The group axiom should hold for this holomorphic variation of group operation and so on. So everything varies holomorphically, and it's a family of groups. That's my definition of group scheme. You don't need a technical definition. So if you know the definition of group scheme, then you can define what's called a G-torsor. So what is a G-torsor? So it is also a smooth family of varieties, complex manifolds, such that your given group scheme G acts on the variety fiber-wise. And the action has to be free and transitive. So what is going on? If you knew the definition, if you already know the definition of principal bundle, then this torsor is a generalization of the notion of a principal bundle. Because if you think about it a little bit, principal bundle, what is a principal bundle? For example, the principal, let's say principal GLM bundle. That means that it morally means that you have all the fibers are GL, and then you have a family of the GL groups, and that's a principal bundle, right? But then it may not have a section, because if you have a section, then that'll force your principal bundle to be trivial. So principal bundle is basically a family of GLs, family of groups without a section. That's a principal bundle. So what is a torsor? A torsor is a family of groups, but even your group can vary. So for example, the GL principal bundle is a family of GLs, but the group GL is fixed. But the torsor is that even your group can vary over the family. So that's the reason why I had to introduce the notion of a group scheme, which is a family of groups. Okay. So let me draw a picture. So group scheme is a family of groups with a section, and intuitively you can consider G-torsor as a family of groups, but without a section, not necessarily. So the typical example is this double covering, cyclic covering of the circle. So consider a genuine, this is not a complex manifold, this is just a circle on a circle. And then you consider this double covering of the circle, and then I claim Y over S is a torsor. Well, first of all, because this is just a Z2 principal bundle, okay? But I told you the principal bundle has a generalization which is called a torsor, and then you can consider also this is a torsor under a constant group scheme, where your group Z2 is not varying. If your group is also varying, that'll be a different, a more complicated torsor. But in this case, this is a principal bundle and also a torsor under group scheme, this constant group scheme.
Is there any simple example where the group varies?
Yes, in our example of an elliptic fibration or Lagrangian fibration.
Oh, sorry.
No problem. Yeah, thank you for the. So yeah, so I'll get into the Lagrangian fibration example soon. So the torsor, if I draw the picture, then the torsor is like the G over S is a group scheme. So this is a family of groups where the purple fiber and the red fiber and green fiber are not necessarily isomorphic groups. Even the groups can vary. And then, you have a G torsor Y over S. That means that all the fibers, this fiber acts freely transitively on this fiber. This fiber, which is a group, acts freely transitively on this fiber, and so on and so on. But then, it may not admit a section. That's exactly the notion of a homogeneous space, principal homogeneous bundle, but where the group also varies. Okay, let's use this notion of a torsor to tackle our situation. Recall that we had a Lagrangian fibration of a hyper-Kähler manifold, which is pi from x to b, and then I pulled out all the singular fibers so that I get an honest torus fibration pi 0 from x0 to b0. Okay, so in the previous examples, 2 examples, if I assume pi 0 has at least one section, then considering that section as a 0 section, you can make this an abelian scheme. Okay, and that gave us the definition of the dual torus fibration, because you can just literally consider the dual abelian scheme. But then if pi 0 doesn't have any kind of a section, then you can't consider it as an abelian scheme. But I want to consider this as an abelian scheme torsor under an abelian scheme. But then to do that, I don't have any abelian scheme to make this a torsor. So constructing an abelian scheme is the first step. And that's actually a theorem proved by Ehrenkin and Fedorov in 2016. So the concept of the theorem is that for any Lagrangian fibration of a hyper-Kähler manifold, there exists a unique abelian scheme making this a P0 torsor. So exactly what you wanted. And this is not a constant group scheme because fiber-wise, like if you have an elliptic fibration of an abelian, like abelian variety fibration, there's no reason why the fibers are isomorphic to each other. The fibers are varying. Complex structure of the fibers varying. So this is not a constant group scheme. This is an honest torsor. It's not a principal bundle. Okay, so here's the picture. So you start from a torus fibration x0 over b0 from a Lagrangian fibration of a hyper-Kähler manifold, and then there exists a unique abelian scheme p0 over b0, making it a torsor. This definitely has a 0 section because it's an abelian scheme, but this one may not admit any kind of section. All right, now we can define our dual torus fibration, at least in our situation. So, well, I'm talking about the same thing again and again and again. Lagrangian fibration hyper-Kähler manifold pi. You pull out all the singular fibers to get an honest torus fibration. And then the next theorem by Ehrenkin and Fedorov is that there exists a unique abelian scheme making this as an abelian scheme torsor, P0 torsor. Okay, right? Notice that this P0 over B0 is an abelian scheme. So there's abstractly a notion of a dual abelian scheme. Okay, so P0 check to B0 check just exists by abstract theory. But then I don't want to take this as my x0 check over B0. So what's the point? The strategy is that I want to, yeah, okay. So here's another theorem. There's just the unique polarization between these abelian schemes, P0 and P0 check. So if you don't know what a notion of a polarization is, okay, it doesn't really matter. I'm not going to use any kind of like technical properties of the polarization. But the thing is that the polarization is basically a surjective homomorphism between group schemes. So this is an abelian scheme. This is a dual abelian schemes. Those are both group schemes, so you can consider a homomorphism between them. And then I want to consider its kernel. This one's surjective. I want to consider the kernel and let K0 be the kernel of this surjective homomorphism between group schemes, so that I can express the dual abelian scheme, P0 check, by the quotient of the original P0 by the kernel. Okay? Then what I can do is that I can mod out the original x0 by this kernel, and that will be my dual torus fibration. So why is this definition a potentially good definition? Okay, so you start from an abelian, the torus fibration x0 over b0. b0 is here, my hyper-Kähler manifold. there exists a unique group scheme P0 making X0 a torsor. Because this is an abelian scheme, by the abstract theory of abelian scheme, there's always a dual abelian scheme, and then some other people's theorem is that there exists basically a unique homomorphism between them. You consider this is a surjective homomorphism between group schemes. You consider the kernel, and then you quotient this out by this kernel, and then they'll make this X0 check a P0 check torsor, and that's good news because that's exactly what we wanted. So the problem of the previous definition of the relative Picard scheme was that the relative Picard scheme is describing this object, and this object doesn't capture the torsor issue. So I need to properly capture the torsor issue to construct this X0 check, and my ingredient for that was just taking a simple quotient. That's it. Okay. So here's the picture. So start from a Lagrangian fibration pi from x to b, throw out all the singular fibers so that you have an honest torus fibration x0 over b0. So this is my Pn, open Zariski open set of Pn, and this is my x0 as torus fibration. So there exists a unique abelian scheme P0 making x0 a torsor. So in particular, they're fiber-wise isomorphic. So this abelian variety fiber is isomorphic to that abelian variety fiber F. This acts simply transitively here. So by the abstract theory of abelian varieties, I can consider the dual abelian scheme P0. So this fiber F and that fiber F check are dual to each other, dual abelian varieties. If you consider a homomorphism from F to F check and consider its kernel, your F check can be recovered from F mod out by K the kernel. So that's exactly what I'm doing on the right as well. Okay, that was the construction of my dual torus fibration. Question about this?
Is it possible to describe the relationship between this construction and the naive construction with the Picard, relative Picard group?
Exactly. Yes, I can do it. So this is the naive construction. It turns out the naive relative Picard scheme is isomorphic to P0 check. This is a naive relative Picard scheme construction. And then if your torus vibration that you started from had a section, that will make this guy a trivial torsor of that guy, so they're isomorphic. But if it doesn't have any section, then it is possible that this guy is not isomorphic to that guy. So the original definition is exactly an abelian scheme, making the dual torus vibration the torsor under that abelian scheme. Yes. Okay, so now we can state the main theorem. So recall that our goal was to start from Lagrangian fibration, throw out all the singular fibers to get a torus vibration, and then dualize the torus vibration to make a dual torus vibration somehow, and then we achieve that. So the final step, there's a final step. We need to compactify the torus vibration in a suitable way to obtain a good Lagrangian vibration, whatever that means. And then the way we have constructed that dual torus vibration was the following. So there exists a unique abelian scheme P0, making this torus vibration X0 a torsor. And then there exists a unique polarization lambda, which is a homomorphism between two abelian groups, abelian schemes, P0 and P0 check. So this is surjective. So if I take the kernel of that, and this is this guy mod out by this kernel, P0 mod out by this K0, and I do exactly the same thing for the X part, not the P part. That will be my dual torus vibration. And the question is, how can we compactify this pi0 check to obtain this thing? And here's the main theorem. So at least for the known types of hyper-Kähler manifolds that I explained in the beginning, K3n, Kumara-n, or greater 10 or greater 6 type, we can achieve that. We can achieve the compactification. And this compactification is actually quite easy because it turns out, at least for known examples, this group scheme K0 over B0 admits a compactification. But then it turns out the compactification is a constant group scheme. So this group scheme that we started from was actually a constant group scheme, it turned out. And then if you have a constant group scheme, then you can obviously compactify into a constant group scheme to a bigger base and obtain another constant group scheme K over B. And not only that, this constant group scheme also acts on the entire hyper-Kähler manifold you start from X. So our dual torus fibration pi0 check can be just compactified into this guy, which is the same quotient, but you just drop the 0 because you can compactify this group scheme into a bigger one. And that turns out to be it. So this X check becomes a hyper-Kähler orbifold because it turns out this quotient becomes a symplectic quotient, what's called a holomorphic symplectic quotient. So this respects the symplectic structure and becomes a hyper-Kähler orbifold. And it emits a holomorphic symplectic form, and this pi check becomes a Lagrangian fibration, holomorphic Lagrangian fibration with respect to the holomorphic symplectic form. So everything behaves super well. And I want to call this a dual Lagrangian fibration, the original Lagrangian fibration that we started from. Okay. So a couple of remarks. If you started from a K3n or a gradient 10 type, for example, if you just started from a honest K3 surface and an elliptic fibration, and if you apply this construction, it turns out this constant group scheme is just an identity group scheme. So you mod out nothing, you quotient it by nothing, and then you obtain the exact same K3 surface that you started from. And in this sense, I want to consider the elliptic fiber K3 surface a self-dual. But if you fall into the generalized Kummer varieties of the Grady type hyper-Kähler manifold, then this group scheme, the constant group scheme, becomes not a trivial group scheme. So you can actually compute what this is, D1 and D2. It depends on the situation. And this is, this just tells you that this is not self-dual. There's some honestly different hyper-Kähler orbifold sort of behaves as if it's a dual Lagrangian fibration. Yes. Okay, questions so far about the main theorem?
So can you say more about self-dual? Do you mean the X check is the same as X and the pi check same as pi? Okay.
Exactly. So because the construction here is that I define the X check by the quotient of the hyper-Kähler manifold that you started from by this group K. And then for K3n and O greater 10 type, this group turns out to be just a trivial group. So that's just a trivial quotient.
Okay, thanks.
That's what we yeah. Thank you. Okay. So, well, I'm definitely not gonna prove this thing here. But let me throw a bunch of keywords for the proof. The proof actually, I honestly wasn't really super interested in this dual Lagrangian fibration stuff when I just started from when they studied the hyper-Kähler theory, hyper-Kähler manifold theory. I was studying more of the study of a relative automorphism scheme of a Lagrangian fibration, and then it turns out one of a consequence of the study of the relative automorphism scheme turns out to be this construction of the dual Lagrangian fibration. So it was a total accident, at least for me. And this kind of thing is related to if you know a little bit about number theory, they talk about Nernst model of elliptic fibrations and so on and so on. This is actually a higher dimensional generalization of that, although we're not working in number fields, but over C, over the complex numbers. So that's related. And then this is like more on the purely hyper-Kähler manifold theory side. So maybe I should just pick on that. Right. So if you study those three and then try to understand more about those three, then the result will pop out. Okay. So that was the main theorem. So I want to wrap up my talk by talking about some more recent results with Mirko, Mauri and Justin Sawon. So my next goal is to justify this dual Lagrangian fibration construction, which turns out to be just a simple quotient construction. I want to justify those two are actually behaving as if they're dual Lagrangian fibrations. So to do that, one of the simplest things that we can verify is to compare the stringy Hodge numbers of X and X check. So we computed both the Hodge numbers of X and the Hodge number of X check for the known examples. That's what we're doing. It turns out if you compute the Hodge numbers of this quotient with the appropriate orbifold structure, then they're still not the same. And we believe this is related to this B field business in the physics literature, which I have no idea about, honestly. But then apparently there's a more algebraic geometry language of this B field, which is called Brauer twisting or gerb. So if you we will try to adopt this Brauer twisting with a gerb definition, and then try to identify both of them. So okay, so let me try to explain how it goes. So so if you see the main theorem, although it was a couple of slides ago, it's really similar to what's called the duality of Hitchin fibrations. So there's like a completely different story. Hitchin fibration people, more related to, I don't know, those kind of people study Langland's program or something like that. Anyway, there's like a completely different set of people studying Hitchin fibration, and they consider this duality of Hitchin fibration. Basically, it means that if you have the group SLN, the simple group, semi-simple group SLN, and the semi-simple group PGLN, and then you consider what's called a moduli space of Higgs bundle, SLN and PGLN Higgs bundle on a given curve. It turns out those two moduli space behave as if they're dual, precisely because this SLN and PGLN are Langland's dual group. Anyway, I'm not an expert on this direction, but there are like a lot of people working seriously on this one. And then the result is the following. So if you have a smooth projective curve with genus at least 2, and then as I said, there's a way to construct the moduli space of SLN and PGLN, what's called Higgs bundles on that smooth projective curve. And then those admit two Lagrangian fibrations independently. Those are pi from Y to B and pi check from Y check to B check. And then the claim is that pi and pi check are dual Lagrangian fibrations in the sense that their general fiber, which is the abelian variety of fibers, are dual to each other. And then it turns out this Y check is a quotient of Y by a finite abelian group K, which is exactly happening in our main theorem. And then furthermore, they have the same orbifold Hodge diamond if you consider this as a twisted one. Twisted is a gerb. So in the algebraic geometry language, this is a Brauer twisting class. So if you consider an appropriate Brauer twisting class, then there is an identification between the Hodge numbers of the Y and the Hodge numbers of Y check, which is the dual part. That's what people have been working about like for more than 20 years, and they made significant theory out of it. So this part, the part 1 and part 2, has a similarity to main theorem, and the third part is obviously missing in the main theorem, and that was our motivation. So we only have the partial result at this point. So the partial result is that there are some instances of the Lagrangian fibrations where these orbifold cohomologies are actually coinciding, at least at the level of Hodge diamond, the numbers. Their Hodge numbers are the same if you count this as an orbifold cohomology. Yeah, so this is certain kinds of Lagrangian fibration where the polarizations are the simplest. But then in general, we believe what we have observed is the case when the Brauer class alpha that is necessary is accidentally 0. So in our case, we believe alpha is 0. And then in general, for more general type of Lagrangian fibrations, we believe there should exist a Brauer class naturally attached to this construction so that there should be an identification of the Hodge diamond between those two up to some Brauer twisting, which is a parallel result, potential conjecture to the Hitchin fibration situation. Yeah, that's it. Thank you for listening.
All right, any more questions for Yoon-Joo? So something that I was wondering about is how you compute K.
How did I compute this, the group? Okay.
Yeah.
Yeah, so and that's a really good question. So, okay, so this main theorem, if you see the statement, I only claim that I proved the main statement for all the known examples of hyper-Kähler manifolds, although this K3 and the graded 10 type turns out to be pretty stupid where the K is just trivial. So, but like in the talk, I've never talked about this argument using the known type assumption. The known type assumption is precisely using in the first statement. And then, so I wrote it as if I have an abstract argument to prove this. But what I really did was for each cases, I computed this group scheme like almost completely. And then I have a different group scheme, which I'll say K prime, obtained from some other hyper-Kähler theory, and then I compare them to, and they turned out to be the same. So this different group scheme K prime is a constant group scheme by construction, and this is a priori not a constant group scheme. And then because we prove they are the same, this becomes a constant group scheme, which is compactifying. So the thing is that the answer for your question is that I just computed it one by one, like because these are all explicit known examples. Computed, of course, there are some more work to do because there's some deformation business, but those are just, not that important. The answer is I just literally computed one by one.
And like you showed us the answers. Were those hard computations or not?
These are non-trivial computations, I believe. These uses moduli space of torsion coherent sheaves on a K3 surface and abelian surface. So yeah, you need a moduli space computation.
I see. Okay. Okay. Any more questions for you and Yoon-Joo?
I have another question.
Yeah, sure.
So Lagrangian fibration induces an integral fine structure on the base. So I was wondering, so you have two Lagrangian fibration. Can you say the two integral fine structure also match with each other?
Yes, those are dual to each other. Those should be dual to each other, at least over. Okay, so I don't know the precise definition of the integral affine structure, but as far as I know, the integral affine structure of the original hyper-Kähler manifold is the cotangent bundle of the. Hold on, am I saying? I'm sorry. Let me take it back. I think what I said was correct. One is a cotangent bundle on Pn because the base has the Pn. And the other one is a tangent bundle. Am I saying it wrong? Sorry, I don't know much about the integral affine structure.
No worry. Thank you.
All right. Well, if there are no more questions, let's give Yoon-Joo another hand.
Thank you for listening.
Yeah, thanks for the great talk.